Hello everyone, welcome to this session on Kubernetes architecture. In this session, we will explore how Kubernetes helps solve real-world challenges in application deployment, scalability, and management. To understand Kubernetes deeply, we need to cover several key topics that will provide a comprehensive understanding of container orchestration. Let's have a look on the topics which we will be covering today as part of this session. The first and foremost would be to understand the modern application challenges. Applications today need to be highly available, scalable, portable, and resilient. However, traditional infrastructure often leads to problems like manual scaling, dependency conflicts, slow deployments, and inefficient resource utilization. We will explore the limitations of these kind of traditional application deployment models and why a new approach is needed. Next, we will be covering the solutions that can help overcome these kind of modern challenges. We will discuss how containers simplify deployments, enhance portability, and improve efficiency compared to the traditional virtual machines. We will also cover a basic comparison between the containers and the virtual machines because I'm quite sure some of you might be wondering that virtual machine may be the answer to all our problems. So we'll cover and go through the different aspects, different features, and do a one-to-one comparison between containers and virtual machines. Once we understand containers, we will introduce Kubernetes, which is one of the most popular container orchestration platform. Kubernetes can automate deployment, scaling, networking, and can also implement self-healing of containerized applications. Once you know the basics, we will do a deep dive into Kubernetes architecture. We will break the entire architecture into the key components, that is the control plane and worker nodes. First of all, let's start with the very basic challenge what we face in most of the applications, that is related to scalability. When I say the word scalability, it would mean that the application is smart enough to automatically scale out or scale in based on the load to make sure the application does not face a performance impact. You can take Amazon as a very good example. I'm quite sure most of us would be doing online retailing on Amazon. So what would happen is that by default, Amazon would be deployed maybe on 5 servers, but on weekends and on festive seasons when the load is very high, automatically the applications would be scaling out, increasing and creating more instances of the applications to handle the more number of incoming requests. And when the festive season is over, automatically the newly created instances would be deleted in an automated manner. So that is the expectation of scalability. Now, if you consider our legacy applications, which can be monolithic, which means that a single process would be using to run multiple application processes, which you can see in this diagram. I have 4 processes, but all of them are combined and running as a single process. Now, with this kind of design, scalability becomes a big problem. So, to be able to make sure that our application is highly scalable, we have to follow the microservice architecture design, in which case, every process should be designed in a way that every application can be scaled without any dependency to any other application process. For example, if I am running a web server with a backend, front end, and due to high load demand, I only want to add more application servers, but only for the backend, I should be allowed to do that without putting a dependency for my front end and a web server because the most of the load would be handled by the backend database. As you can see over here, once we have isolated all our processes, we can easily scale out all my application processes independently without relying or putting any dependency on fellow processes. In this particular case, I can see that my red circle processes are properly scaled out on different servers without any dependency. But this was only possible when I was able to remove the dependencies from my monolithic application. Next, one of the other problems what we face with the monolithic application is that the processes are highly dependent on different set of libraries. So if you can imagine, if I have 4 processes running, it is very much possible that all these 4 processes are dependent on different set of libraries and each library can be of different versions. Now, this creates a scenario of conflict wherein the end user has to spend a lot of time handling the conflict and the dependencies. So we have to make sure that we are designing our application in a way that there is very minimal or no dependency at all between the applications, which is when we can call them an actual microservice. Now, these were the problem statements. So, what are the solutions? As of today, we have two possible solutions. Either we can go for a virtual machine based approach, or we can go for a containerized model. Now, first of all, we can isolate all the applications into an individual virtual machine. As you can see on the screen, this is how a virtual machine would work. We would have a bare metal hardware, on top of which we would be having an host operating system, which can be either Linux, Windows, or any other operating system. It doesn't matter. What matters is that on top of that operating system, we need to have an hypervisor installed. The hypervisor is a software which is bundled as part of maybe Oracle VirtualBox, VMware Workstation, vSphere ESXi, Hyper-V, and there are many other softwares which provides us this hypervisor solution. Now, once we have an hypervisor installed on top of an host operating system, we get an interface by the hypervisor software to create these virtual machines. Here I have created a separate OS which has its own set of libraries and dependencies, and in this VM I would be running only Node.js. Similarly, I have created 3 more virtual machines and I have made sure that only the respective applications are running in those virtual machines. So with this, one problem is solved. I was able to isolate the libraries and dependencies which was scattered across the applications. But does it solve all my problems? Because it has introduced one more problem. Since every VM has its own operating system, the boot up time would be very slow because it has to load all the system services. Next, the resource requirement would be very high because the system itself would use quite number of CPU, RAM, and storage. Now imagine my only requirement was that I wanted to run my application in an isolated manner. But to do so, I would end up investing a lot of amount in the resources as well as maintaining the hardware. Next, let's explore the other solution what we have, that is using containers. Now the container design also looks pretty much same as what we had in virtual machine. We have a bare metal machine which can be anything. It can be a physical server or a cloud or anything, doesn't matter. On top of that, we would be installing an operating system. Now the operating system over here plays a crucial role because the shared kernel file system would be one of the key aspects for the container to run properly. Now in this particular case, I would assume that the operating system running over here is based out of Linux. So I will have a Linux kernel running over here. On top of that, I will install a container management tool so that it simplifies the overall container management for me. Now the container management tool can be either Docker or Podman. Doesn't matter. We will discuss this in depth maybe in the upcoming tutorials. Now on top of Docker, we will be creating separate set of containers and each container will be hosting one individual applications. Now, if you see over here, the basic problem what we had earlier is solved here as well, wherein each application is running independently without any dependencies towards any other application. So my Node.js does not know about SQL Server and both of them are maintaining their libraries and dependencies within their container. But with this, we have solved one more bigger problem. I don't have a guest OS running inside the container anymore because the container is basically running with a minimal file system from the operating system. Plus it is using the Linux kernel to make sure that all the processes are isolated and to be able to run in an individual isolated container box. So that is a very big advantage what we are getting over here in container compared to VirtualBox. Now let's do a one-to-one comparison to understand the overall difference and then maybe we can make a decision which solution is the best fit for our requirement. Now first of all, considering the architecture, as I had shown in the image, virtual machines expect a complete guest OS to be installed inside a VM to be able to run the application. Without this OS, VM cannot start. But that dependency is not there with the container. Container is basically using the host OS plus it is using the kernel and a very minimal file system to be able to start the container. Now considering the boot time, since the VM is using a proper OS, it has to start all the system services every time it is coming up, which can delay the overall bring up process. Now coming to containers, since it only has to make sure that the application is started and stopped, so the overall boot up time basically depends only on the application startup time. It has no other service which it has to make sure that it is up. In terms of resource usage also, most of the resource would be used by the operating system again because it would need dedicated amount of CPU, RAM and storage to store all the system libraries, files and to start the system services. But in this case, since we do not have any operating system, it is pretty much lightweight, and the only resource we have to worry about is the application consumption. In terms of scalability, both virtual machine and containers are scalable, but again, other problems or the other features come into a factor. Now, in terms of virtual machine, if you want to do a scale out based on the load, you again have to consider that you would need more amount of resources. The boot up time would be higher whenever we are doing a scale out operation. Now, in compared to this, in a container, when we are doing a scale out, it will be coming up instantly because it will not waste any time bringing up any other resources other than application. In terms of portability, the virtual machines are dependent on the hypervisor, and there are a couple of hypervisor available as of today in the market, such as VMware, Hyper-V, KVM, etc. While containers are platform independent, you just have to make sure that you have installed a Docker or Podman daemon, and on top of that, you would be allowed to create containers without any further dependencies. In terms of security, I would say VM has an upper hand compared to containers, because in VM, since you are bundling the entire operating system, you get more control on the kind of security you want to put for that particular virtual machine. While in containers, since we don't have that kind of flexibilities and a container normally runs without any privilege or capabilities, there is very little kind of security what you can implement inside a container. So if you want to secure your container, you have to make sure that your host OS is perfectly secured in terms of every aspect, which can be sysdl, SC-Linux, firewall, and any other aspect. So this has to be controlled on the host level rather than the container level. In terms of use cases, the virtual machine are mostly used for monolithic applications where you have a big applications and you have a lot of dependent processes and all of them are tightly coupled. In such cases, I would suggest for you to go with virtual machine. But if you have a possibility to split the applications into microservices such that all these application processes can start and function independently, in such cases, I would suggest you to go with the cloud native approach using containers. Now that we have covered the basic difference between containers and virtual machines, you may get this one question that can I run different variants of operating system on top of Docker? Now, normally when you're running a Docker daemon or a Podman daemon on top of a Linux OS kernel, then it becomes sort of mandatory that you are only allowed to run Linux-based containers. You cannot run a Windows or any other variants of container on top of Linux OS kernel. And if you try to do so, the same would fail. Now, this is by design. This is because Windows and Linux use different types of kernels. Linux containers expect a Linux system call interface, which Windows does not provide. Similarly, Windows containers require Windows kernel APIs, which are unavailable on Linux. So you have to make sure if you're going for such mixed mode approach, you should have an environment where you have installed a Windows based environment, and on top of that you can create Windows based container. But if you're having a Linux based operating system on which your Docker daemon is running, then you can only host Linux based containers on top of that. Now that we are familiar with the containers, let's jump into the next step, that is Kubernetes. Now what is Kubernetes? If we go for the official definition, Kubernetes is an open source platform that automates deployment, scaling, and management of containerized applications. Now, what does this mean? You have to think Kubernetes as an orchestrator. It is sort of acting as a wrapper, and it is giving you a lot of flexibility to control and manage these containers, because containers are a very independent entity. So we need Kubernetes to be there and manage these different set of containers. Because if you imagine a large application which has maybe more than 10 application containers, you would need one orchestrator who can basically help you scale out, scale in all these application containers, perform an automated recovery, and do a lot of other things. Now, when I say Kubernetes acts as a container orchestrator, what would that mean? Now, Kubernetes is basically formed out of two main components. One of them is master node, which we also refer to as control plane, and the other component is worker node. We'll cover these two topics in much more details in the upcoming slides, but for the time being, let's focus on the orchestration part. What happens basically is that the master node has the privilege to control and manage all the other worker nodes. Now imagine you have a web server front end with a backend database which is installed across multiple Kubernetes worker node clusters. But as and when the overall load increases, more users are connecting towards your web server, obviously you would expect that your application is able to handle the load. In such case, master node will automatically start the orchestrations and it will start deploying the application server across the available worker nodes. As you can see over here in my case, automatically new applications are getting deployed. Now we can also enhance this feature to also automatically deploy new worker nodes, and on top of that you can start deploying the applications. But that is only possible if the underlying infra supports that kind of feature. For example, if you have set up your Kubernetes cluster on a cloud environment such as AWS, Google Cloud, in such cases, you get this flexibility that if you are running out of worker node, then you can do the configurations in a way that when the load increases, automatically new worker nodes would be deployed and the applications would be automatically deployed on those worker nodes. And when the load is decreased, automatically the application number would be reduced and the worker nodes will be deleted. Now let's jump into the Kubernetes architecture. As I also explained in my previous slide, there are two core components which basically forms the Kubernetes cluster. One of them is referred as master node or control plane, and the other one is referred as worker node. The master node is made out of etcd, kube-apiserver, kube-scheduler, and controller-manager, whereas the worker node is made out of kubelet, kube-proxy, and container runtime. Let me explain you what each of these component does and how they basically communicate with each other. The API server is the entry point for all communication within the Kubernetes cluster. It basically validates requests, process commands, which you are giving via kubectl or via basic API calls, and it is responsible for interacting with all other components. As you can see over here, almost all the components are reaching out to API server. So this is the basic entry point for almost all the processes except etcd. So what is etcd? It is a distributed key value store that stores the entire Kubernetes cluster state. Basically, if you have deployed some keyed resources such as pods, deployment, so the status of all those pods deployments would be stored inside the etcd. This is basically referred as the desired state of the target keyed resource. Now in future, tomorrow, if you have deployed a backend database pod and it was deployed successfully, then that status would be immediately stored inside the etcd. I will be covering this point in much more detail in the upcoming slides where I will be explaining you the overall flow of pod deployment. Next is the scheduler. The scheduler is responsible for deciding which worker node will run a new pod. So whenever you deploy a pod or whenever a pod crashes and a new pod is coming up, the job of the scheduler would be to find the most adequate and available worker node where those pods can be deployed. It evaluates on multiple parameters such as the CPU, memory, taints, tolerations, node selectors, etc. All these variables, and based on that, it makes a decision that okay, pod A should be deployed on worker node A. Next is the controller manager. The controller manager would be continuously monitoring the cluster state and it ensures that it matches the desired state. Now, if you recall the word desired state I had used earlier when I said that the complete status of all keyed resources are stored inside the etcd, and that is what is termed as desired state. So it is the job of the controller manager to check the deployed keyed resources and compare it with the desired state as available inside the etcd. For example, if a pod fails, the controller manager would immediately detect it and instruct the Kubernetes to create a replacement pod. This is done as part of automatic failover and recovery procedure. Next, let's jump on to the worker node components. Worker nodes are where actually applications would run. Each worker node includes something called kubelet, kube-proxy, and container runtime. Kubelet is a very small agent that runs on each worker node and it communicates with the API server. It ensures that the containers are running as expected and it reports back the node's health. For example, when the API server instructs a worker node to create a pod, kubelet ensures that the container starts properly. The next is container runtime. The container runtime is the software that runs and manages containers inside Kubernetes. Now, Kubernetes supports multiple container runtimes, including Docker, Containerd, and CRIO. For example, when a pod is scheduled, the kubelet asks the container runtime to pull the image and then start the container. So that is one of its job. Next is kube-proxy. The main role of the kube-proxy is to manage networking and load balancing between the pods. It ensures that containers can communicate with each other and with the outside world. For example, if I have a backend Kubernetes service which needs to talk to a front-end service, kube-proxy would be routing that traffic correctly. I will be giving demo to all these components in the upcoming tutorials so that it is very much clear and you understand with a practical example how this component would work. Next, let me show you the overall workflow on how the different components what we just discussed in the previous slides would be communicating with each other when we are deploying a very fresh pod into the Kubernetes cluster. As you can see, I have created blocks with all the components which we discussed earlier, which includes API server, etcd, scheduler, kubelet, container runtime, kube-proxy, and controller manager. Now, for example, user gives a request to create a new pod. After that, what would happen? Now, once the user sends a request to create the pod, the API server, since it is the main control hub, will process that request. The API server will store the desired state in the etcd. At this particular stage, the desired state is what would match from the YAML file. For example, in the YAML file, if you have given that there should be total 2 replicas and maybe the resources would be 1 vCPU, 1 GB memory, then all these informations would be stored in the etcd. Next, the scheduler will be responsible for selecting and identifying a worker node to run that particular pod. It will evaluate the available CPU and the memory resources on all the worker nodes, and it will also evaluate many other parameters such as node affinity rules, taints, tolerations, etc. Based on all these, it will be basically assigning the best available worker node, and then after that it will notify the API server of its decision. Then API server will send an instruction to the kubelet running on the assigned node to deploy the pod. Before pulling the container image, the kubelet will send a request to the CNI plugin, that is Container Network Interface plugin, to set up networking for the new pod. The CNI plugin assigns a unique IP address to the pod so that it can communicate within the cluster or outside the cluster. Once networking is configured, then the kubelet will instruct the container runtime to pull the required container image, which will be required to start the container. Next, the container runtime downloads the image and starts the container inside the pod. When the container starts successfully, the kubelet will report back to the API server that the pod is now in running state. Next, immediately the controller manager will start monitoring the pod health to ensure that it remains running. Next, the API server will send a confirmation to the controller manager that yes, the pod is healthy and it is up and running. At the same time, the API server will also send a request to the etcd to update the actual state of the deployed resource so that the etcd always has the latest status of the deployed resources. Next, let's explore what would be the flow across all the Kubernetes components during a pod failure and an automated recovery. Now, as also we told and discussed in the previous slides, controller manager would be always monitoring the cared resources which were deployed. Now, if a pod crashes due to application failure, node failure, or any other issue, the controller manager will detect this failure automatically. Next, the controller will report this failure to the API server. Once API server gets to know about the failure, it will immediately inform etcd about the failure so that the current state is updated inside the data store. This will help Kubernetes determine the actions required to restore the desired state. Next, the controller manager will send a request to the scheduler to schedule a replacement pod. Now from this stage, the steps would be pretty much same what we discussed in the previous slide. The scheduler will evaluate the available worker nodes to determine where the new pod should be deployed. Based on the resource availability and all other parameters, it will make a decision to either deploy the pod on the same or new worker node. And once it has finalized, it will inform the API server of its decision. The API server then sends the instruction to the kubelet running on the assigned node to deploy the new pod. Before the container starts running, Kubernetes assigns a network configuration to the pod. The kubelet will send a request to the CNI, that is Container Network Interface plugin, to set up networking for the new pod. The CNI plugin assigns an IP address to the pod, ensuring that it can communicate with other services once it is running. After the network is configured, kubelet instructs the container runtime to pull the required container image from the provided registry. Next, the container runtime will start the container inside the pod. Once the container is running, the kubelet updates the API server to report the pod status. After the pod reaches the running state, kubeproxy configures network routing and service discovery. Now, since this is a pod failure and recovery scenario, it is very much possible that there are other instances of the pod replicas which are already deployed, and maybe someone else is communicating with these pods with a Kubernetes service or any other kind of front end. So the kubeproxy ensures that the traffic can reach to the new pod and updates the service endpoints if necessary. Finally, the controller manager verifies that the desired state has been restored and it will update the etcd with the new cluster state. Now at this stage, the etcd contains the latest status of the deployed resources and an automatic recovery has happened successfully. Now I hope by the end of this session, you should be familiar with the basic building blocks and the concepts involved with Kubernetes and containers. Now, on top of Kubernetes also, we have many other terminologies which you may come across, such as Helm, Kubernetes operators. We will be discussing about these in the upcoming tutorials, and I'll be creating separate ones because I don't want to make this as a very large video. So for the time being, let's conclude this tutorial. And if you have any questions or concerns or feedback related to the Kubernetes architecture, please feel free to leave your response via the comment section and I'll try to get back to you. Thank you.